Empty space will kill you. Not immediately, not today. But if the calculations are correct, if our theories about what lurks in the vacuum are right, then every cubic centimeter of empty space around you contains enough energy to boil every ocean on Earth instantly. I discovered this accidentally in 1915, buried in the mathematics of general relativity, a term that refused to go away, a constant that seemed to represent the energy of nothingness itself. I called it my greatest blunder. But I was wrong. It wasn't a blunder. It was a glimpse into something so strange, so fundamentally disturbing about reality, that even today, over a century later, physicists wake up in cold sweats thinking about it. They call it the vacuum catastrophe, the most spectacular failure in the history of science. Our best theories predict that empty space should contain so much energy that the universe should have collapsed the moment it began. But here we are, alive, breathing, completely unaware that we're swimming in an ocean of impossible energy. Let me show you what I mean. You think empty space is empty, don't you? Vacuum, nothing, the absence of everything. Take away all the air, all the particles, all the light, all the matter, and what's left? Nothing, right? Wrong, catastrophically wrong. Even when you remove everything, every atom, every photon, every particle you can imagine, space itself is still there. And space, as I discovered, is not nothing. Space is something. It can bend, it can stretch, it can ripple like the surface of a pond. Gravitational waves prove this. We've measured space itself vibrating as massive objects accelerate through the cosmos. But if space can bend and ripple, then space has properties. It's not just a passive container holding things, it's an active participant in reality. And here's where it gets disturbing. Anything with properties can store energy. In 1915, I wrote down the equations for general relativity. Beautiful equations that describe how matter curves spacetime, and how curved spacetime tells matter how to move. But there was a problem, a mathematical problem that kept me awake for months. The equations didn't want to give me a static universe. Every solution I found led to a cosmos that was either expanding or contracting. But I knew, I was certain, that the universe was eternal and unchanging. The stars were fixed in their positions. The cosmos was stable. So I added a term, a small constant multiplied by the metric of space-time itself, the cosmological constant, lambda. It represented the energy density of empty space itself, a repulsive force built into the fabric of reality that could balance gravity and keep the universe static. I thought I was fixing a mathematical inconvenience. I was actually discovering that the vacuum itself has energy. But here's what I didn't realize at the time. Here's what would have terrified me if I had understood the implications. That cosmological constant wasn't arbitrary. It had to have a specific value. And that value, according to quantum mechanics, should be impossible. Let me explain. Quantum mechanics tells us that empty space isn't empty. It's seething with activity. Virtual particles are constantly popping into existence and annihilating each other. Electron-positron pairs, photon pairs, all manner of particle-antiparticle duos flickering in and out of reality so quickly that they exist below the threshold of measurement. This isn't speculation. This is observed, measured physics. We can detect the effects of these virtual particles. The Casimir effect proves two metal plates placed close together in a vacuum will attract each other because the virtual particles between the plates are constrained. There's literally less room for them to exist. The vacuum outside the plates pushes them together with measurable force. But here's the problem. If virtual particles have energy, and they must, because energy and mass are equivalent, and these particles have mass, then the vacuum itself has energy. A lot of energy. How much energy? Let me do the calculation for you, and I warn you, the answer will disturb you. Each virtual particle contributes energy equal to 1/2 times Planck's constant times its frequency. That's the zero-point energy, the energy that exists even at absolute zero temperature, even in perfect vacuum. Now, quantum field theory tells us there are virtual particles at all possible frequencies, all of them, from the lowest possible frequency all the way up to, well, that's where the problems start. Up to what frequency? If you integrate all the way to infinite frequency, You get infinite energy density in the vacuum. Clearly impossible. So physicists impose a cutoff. They say virtual particles only contribute up to some maximum frequency. But what frequency? The obvious choice is the Planck frequency. At energies higher than the Planck scale, our theories break down anyway. Space and time themselves become uncertain. So let's cut off at the Planck frequency. Do the calculation. The energy density of empty space comes out to be 10 to 1113 joules per cubic meter. Let me put that in perspective for you. The energy in 1 cubic centimeter of empty space, a volume smaller than your thumbnail, would be enough to power the entire Earth for trillions upon trillions of years. The energy in a coffee cup of vacuum would be enough to boil away every ocean on the planet. But that's not the worst part. The worst part is what this means for the universe. You see, energy has gravity. Mass and energy are equivalent. Remember, E equals mc squared. And gravity couples to energy just as it couples to mass. If the vacuum really contains 10^113 joules per cubic meter, then the vacuum has enormous gravitational effect. How enormous? The energy density I just calculated is about 120 orders of magnitude larger than what we observe. The vacuum should be so dense, gravitationally speaking, that the universe should have collapsed into a black hole the instant it began. Space itself should be so curved by its own energy density that nothing, not matter, not light, not even the possibility of existence, could survive. But here you are, reading these words. The universe clearly didn't collapse. Something is very, very wrong with our calculation. This is the vacuum catastrophe, the greatest discrepancy between theory and observation in the history of science. Our best theories of quantum mechanics apply to the vacuum give an answer that's wrong by 120 orders of magnitude. 120 zeros wrong. To put this in perspective, if you predicted the distance from Earth to the Sun and you were off by 120 orders of magnitude, your prediction would be wrong by a factor larger than the number of atoms in the observable universe. This isn't a small error. This isn't close enough for government work. This is catastrophically, incomprehensibly wrong. And yet, here we are. The universe exists. Space is not collapsed. You can move your hand through what appears to be empty air. The vacuum catastrophe predicts that this should be impossible, but reality disagrees. So what went wrong? Where did our calculation fail so spectacularly? The honest answer is, we don't know. We have no idea. This is one of the greatest unsolved problems in physics. We have theories, guesses, desperate attempts to patch the mathematics, but no real understanding. Some physicists propose supersymmetry. The idea is that for every particle, there's a corresponding superparticle with opposite quantum property. When you calculate the vacuum energy, the contributions from particles and superparticles cancel each other out exactly. Zero vacuum energy. Problem solved. Except we've never found a single superparticle. The Large Hadron Collider has been looking for decades. Nothing. If supersymmetry exists, it's hidden at energy scales we can't yet reach. Others propose that we're thinking about this wrong. Maybe virtual particles don't really exist. Maybe they're just mathematical artifacts of our calculation method. Maybe the vacuum is truly empty and we've been chasing ghosts. But this doesn't work either. We can measure the effects of virtual particles. The Casimir effect is real. The anomalous magnetic moment of the electron depends on virtual particle interaction. Hawking radiation from black holes depends on virtual particles near the event horizon. You can't just wish them away. Some physicists get more exotic. Maybe the vacuum energy is there, but it's hidden in extra dimensions. Maybe our three-dimensional space is like the surface of a balloon, and the vacuum energy exists in higher dimensions we can't perceive. Maybe the total energy of the universe is exactly zero. Positive matter energy, cancelling negative gravitational potential energy, and the vacuum catastrophe is telling us something profound about the deep structure of reality. Maybe. But these are all just guesses. Elegant mathematical guesses, but guesses nonetheless. The truth is darker. We understand almost nothing about the vacuum. The space around you, the emptiness between atoms, the darkness between stars. It's all completely mysterious. We can measure its properties, we can detect its effect, but we cannot explain why it behaves the way it does. Think about this for a moment. You are surrounded by empty space right now. The distance between the nucleus of an atom and its electron is mostly vacuum. Your body is mostly empty space held together by electromagnetic forces. The room you're in is mostly vacuum with a thin scattering of gas molecules. And that vacuum, that supposed nothingness, contains mysteries that have baffled the greatest minds in physics for over a century. Every breath you take moves through space whose energy content we cannot calculate correctly. Every step you take moves through a medium we do not understand. This should humble you. We've split the atom. We've mapped the human genome. We've landed on the moon and sent robots to Mars. But we cannot correctly predict the energy density of empty space. We cannot explain why the universe doesn't collapse under the weight of its own vacuum. But here's what disturbs me most about the vacuum catastrophe. It's not just an academic puzzle. It has real implications for the future of physics, the future of our understanding of reality. You see, the vacuum catastrophe is connected to the dark energy problem. Astronomical observations show that the expansion of the universe is accelerating. Something is pushing space apart, overcoming gravity. We call it dark energy, but we don't know what it is. The simplest explanation is that dark energy is vacuum energy, cosmological constant, the energy of empty space itself, providing a repulsive force that drives cosmic acceleration. But if vacuum energy causes dark energy, then we're back to the vacuum catastrophe. Why is the vacuum energy so small? Why doesn't it collapse the universe? How can the same physics that predicts 10⁻⁻⁸ joules per cubic meter also explain the tiny amount of dark energy we actually observe? We're missing something fundamental, something basic about the nature of space, time, energy, and existence. The vacuum catastrophe is a giant neon sign, flashing, "Your theories are incomplete," but we can't read what it's trying to tell us. And this affects everything. Every equation in physics assumes we understand the vacuum. Every prediction about particle physics, cosmology, quantum mechanics, they all depend on getting the vacuum right, but we don't. We're building the edifice of modern physics on foundations we don't understand. But let me tell you about the experiments that make this even more disturbing. The evidence for virtual particles isn't just theoretical. We can see their footprints everywhere. Take the Lamb shift. In the 1940s, physicists discovered that hydrogen's electron energy levels aren't exactly where theory predicted. There's a tiny shift that shouldn't exist if the vacuum were empty, but virtual particles near the electron would modify its energy. The calculation matches observation perfect. So virtual particles are real. Their effects are measurable. The vacuum is definitely not empty, which makes the vacuum catastrophe even more puzzling. Here's another disturbing thought. The vacuum catastrophe might be telling us that our entire approach to physics is wrong. We think of particles as fundamental objects, little billiard balls bouncing around in empty space, but quantum field theory suggests something different. Maybe there are no particles at all. Maybe everything is just excitations in underlying fields. These fields permeate all of space. What we call particles are just ripples, waves, disturbances in these fields. If this is true, then the question, what is the energy of empty space, becomes meaningless. There is no empty space. There are only fields. The vacuum is the ground state of all the fields. But this still doesn't solve the vacuum catastrophe. If anything, it makes it worse, because now we have to explain why the ground state has such a tiny energy density. In fact, there's evidence suggesting the Higgs field exists in what we call a false vacuum. It's stable, but might not be the lowest possible energy state. If the Higgs field transitions to the true vacuum, it would destroy everything. This is called vacuum decay, one of the most terrifying scenarios in physics. Sometimes I wonder if this is what it felt like in the late 1800s. Classical physics seemed complete. Maxwell's equations described electricity and magnetism. Newton's laws described motion and gravity. Thermodynamics described heat and energy. Everything seemed to fit together, except for a few small problems. The blackbody radiation curve didn't quite match theory. The Michelson-Morley experiment gave an unexpected result. Mercury's orbit precessed slightly more than Newton predicted. Small problems, tiny discrepancies, nothing that seemed to threaten the entire structure of physics. And then Planck discovered the quantum. I discovered relativity. The small problems demolished classical physics and rebuilt our understanding of reality from the ground up. The vacuum catastrophe feels like those problems. It seems technical, mathematical, abstract, but I suspect it's pointing towards something revolutionary. Consider the implications if we're wrong about the vacuum. If empty space really does contain enormous energy, but we simply can't detect it. Just 1 cubic meter would contain enough energy to power civilization for millions of years. Of course, this would be incredibly dangerous. Remember, if you could extract vacuum energy, you'd be locally lowering the energy density of space. This might trigger a vacuum decay event. Here's what keeps me awake at night. We're living in a universe we don't understand. Every breath you take, every step you walk, every thought you think, it's all happening in a medium whose fundamental properties remain mysterious. But here's the most disturbing possibility. What if the vacuum catastrophe is correct? What if empty space really does contain 10.13 joules per cubic meter, somehow perfectly balanced? Think about what this would mean. Every point in space would be a reservoir of infinite energy, held in perfect balance. The tiniest fluctuation would unleash energies that could vaporize galaxies. This is why I can't let go of this problem. Somewhere in the mathematics is a secret about existence itself, a clue about why there is something rather than nothing. When we finally solve the vacuum catastrophe, and I believe we will, it won't just be a triumph of theoretical physics. It will be a revelation about what it means to exist in a quantum universe. Until then, we live surrounded by mystery. The empty space around you, the vacuum between atoms, the darkness between stars. It's all a riddle we cannot solve. Every moment of your existence is a testament to forces we don't understand. And that, perhaps, is the most profound lesson of the vacuum catastrophe. In a universe where empty space might contain infinite energy, we are witnesses to mysteries beyond our comprehension. We are children of the vacuum, born from quantum fluctuations we cannot fully fathom. Every breath we take, every thought we think, is made possible by the deepest secret in physics, why nothingness allows us to exist. The vacuum catastrophe feels similar. It seems like a technical problem, a calculation gone wrong, a mathematical curiosity, but I suspect it's telling us something profound, something that will revolutionize physics the way quantum mechanics and relativity did a century ago. What if space and time are not fundamental? What if they're emergent properties of something deeper, something we haven't discovered yet? What if the vacuum catastrophe exists because we're asking the wrong question, making the wrong assumptions, missing the real nature of reality? I don't know the answer, but I can feel it coming. Somewhere, in some laboratory or university office, someone is working on the problem that would unlock the mystery of the vacuum. And when they do, when they finally understand why empty space behaves the way it does, everything will change. Physics will be reborn. Our understanding of the universe will be transformed. The vacuum catastrophe will no longer be a catastrophe. It will be a clue, a breadcrumb on the path to a deeper truth. Until then, we live with the mystery. Every day, every moment, surrounded by empty space that contains secrets we cannot fathom. The vacuum is our constant companion, and we understand it not at all. That's the true vacuum catastrophe. Not that our calculations are wrong, but that we're so fundamentally confused about the nature of nothingness itself. In a universe where empty space might contain infinite energy, where the absence of everything might be the most powerful presence of all, we are children playing with equations we barely comprehend. And that, my friends, is both terrifying and wonderful, because the universe still has secrets to tell us. The vacuum is still waiting to reveal its mysteries, and the greatest discoveries in physics are yet to come.